Welcome to Trend-Adjusted Exponential Smoothing Method. If you liked exponential smoothing models, this is even more fun because now we incorporate a trend, and the trend is itself an exponential smoothing model. Sometimes this trend-adjusted exponential smoothing method is called the double exponential smoothing method because not only do we use the exponential smoothing method to find an average or a forecast for the series or for the data, but we also use the exponential smoothing model to find a value or a forecast for the trend. Okay? So we saw when we were dealing with our Apple data, and we were missing something. We were consistently under forecasting Apple demand. And when that happens, one of the reasons, there could be several reasons, but one of the potential reasons is that we're missing a trend. Okay? And that means that trend can be, trends are just a systematic or an overall pattern change. Either the pattern, the overall pattern is up or the overall pattern is down. Now, there could be fluctuations as you go up, and could be fluctuations as you go down. Right? We're not talking it has to be nice and pure and clean, but that the trend overall is up, or the trend or the pattern overall is down. Okay? And so we have a way to incorporate that with the trend-adjusted exponential smoothing model, to bring that lag in there so that our errors don't have that. We try to minimize that bias as well. Okay? So again, it is sometimes called a double exponential smoothing model. So as a result, because we're using an exponential smoothing model both to estimate the series itself as well as to estimate the trend, we will have two smoothing constants. So when we were just doing the single exponential smoothing model, we just had alpha. That was our only smoothing constant. Now that we're going to both estimate the series itself, alpha stays, but we're also going to estimate the trend as well. So that means we're going to need a second exponential smoothing constant. And so here's our model, and I know it looks a little bit messy, but let's just break it down a little bit. The A now is the average, is sort of the average, and that is like our forecast for the smoothing model, right? We had an alpha, a smoothing constant, times by the demand, okay? So alpha times by demand, and then 1 minus alpha times by AT minus 1, TT minus 1. Average for the previous period plus the trend for the previous period. Now, if we kind of skip ahead a little bit and we look and see, look at the forecast. The forecast is where I take that average plus add it to its trend. So I take the average, which would be the forecast in the old way, and then I add the trend, and that's my forecast for the next period. Well, if I look at those subscripts really carefully, I notice something, that AT minus 1 plus TT minus 1, right, which is in the average formula. And then I look at, okay, what's FT plus 1 equals to AT plus TT. Well, if I subtract 1 from all of these, what do I get? I get FT equals to AT minus 1 plus TT minus 1. So that second value in the brackets there is nothing more or less than the forecast for the previous period, which is exactly what we did with the exponential smoothing model before. Okay? So that stays the same. So no big change there. Okay, couple little bit of notational changes, but conceptually the same. The trend. Now, the trend is trying to capture differences, right? So when we see, okay, well, the trend is, we look at the average from this period minus the average from the last period, right? That's a difference. That's a difference. And we're trying to capture this difference, right, with the trend. And we have an exponential smoothing constant called beta in that regard. So we have the difference in the most current couple period and the period before it, plus a factor times by the previous estimate for the trend. Which was these trends are forecasts, right? So it's like the previous forecast. So we look at the current difference plus adjustment for the previous differences, right? The trend, the trend before this current period. So we can kind of see the elements of the basics of the exponential smoothie model just being applied twice here. Now, this trend-adjusted exponential smoothie model, like I said just a couple seconds ago, is sometimes called a double exponential smoothie model. It does have other names as well, so you sort of want to keep track of what is happening here. So if you ever encounter this in the future, it may not be going by the name trend-adjusted exponential smoothie model. It may have a name. It may have a name related to some of the folks that originally came up with it, and so on. So it goes by many aliases, but look at what's going on and relate that to what's going on if you see it represented by another name. Okay, so we got to keep our sort of mentally flexible, because then the names may change, but because we're smart, we see that name change, and we are not fooled. We are not intimidated. Okay, and like I said before, here's all the key variables and AT, TT, FT plus 1. It's the forecast, which is what we ultimately want to do. Sometimes when we look at these little formulas, we go, holy cow, big brain sweat to get the A, big brain sweat to get the T, and we forget I got to add the two of them up to get the forecast, which is what I want in the first place, because, after going through the brain sweat to find the average and going through the brain sweat to find the trend, you forget the little easy step that's the most important of it all, and that's just to add the two of them together to get that forecast. Okay, let's do some repetition so that we can establish a pattern. Okie dokie. Okay, there we go. Let's go up to the previous slide so we can move things around and see what's going on. Okay, so first step in this process is where can I start? Where can I start in all this? And it becomes a little tricky in that regard. Now, I know from my exponential smoothing experience that if my data starts at 2014, I can't do a forecast for 2014 because that depended on something from 2013. And then I start to think, well, can I do a forecast for 2014 with this model? And I go, I'm not sure, right? And so I look, hey, what's that forecast for 2015 look like? Well, that requires an average from 2014 plus the trend from 2014. Okay. The average from 2014, I see, depends on and it will depend on a forecast for 2013, right? I'm just looking at my formula here. Nothing more than looking at that formula. And the trend itself will also depend on averages from 2000 and it'll depend on an average from 2014 and an average from 2013. Okay, so that's a little tricky here because I don't have that 2013 data. I can make sort of a fudge thing for the forecast for 2014, but I'm starting to get a little bit iffy, and then I like to have a little extra. How would I come up with a trend, right? I think of a trend as differences. I'd like to find the difference between something, so maybe the difference between two demands to sort of get things rolling, so that I sort of have some idea. I could start this in 2014, but I would be making big leaps as far as both the AT. Okay, I can do that. And then I got to make another big leap as far as the TT. And I go, maybe I don't want to do that. And this is all judgment. I'm not saying this is the best way to do it, but I like to kind of maybe have at least two demands so that I can see what that differences look like between those two demands, so I can come up with maybe a more reasonable starting point for the trend. It's not going to be the correct starting point for the trend, but maybe a little bit more reasonable than just making something up. But again, judgment method can still apply when we can start one period earlier if we like. Okay, we'd be making a lot of judgments. So let's look at making a forecast to start off with 2016, right? And that way I'll have a little bit more input on the trend, right? Because I'll be able to then look at the difference between revenue in 2014 and revenue in 2015, and get at least an initial non-murky estimate for what the trend could possibly be. So to find the forecast for 2015, I still need an average for forecast for 2016. I need an average for 2015. Now, in this case, I can just make it the demand for 2015. This is sort of just our bootstrap starting point. No matter what we do, we need to have some starting point that involves us making some leap of judgment, or in this case, sort of like a naive model estimation. And we can't get around that. I'm just trying to minimize how much of this we have to do for the trend, okay? So again, there's judgment involved in this. So, and we can make that equal to, what was the demand for the 2015? 233.72. Our trend for 2015, we'll just make it for the difference in demand. So the demand for 2015 minus the demand for 2014, which equals to 233.72 minus 215.64. Just remember, these are all in billions of dollars. And the trend is $18.08 billion. Okay. And so at the end of all this, our forecast for 2016, just simply 233.72 plus 18.08, and the forecast at our initial very, 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 very first forecast, 251.80. Okay. And now I keep rolling this up. I mean, I can find the error for this as well, error for 2016. And that's just the demand. What was the actual demand for 2016? It was 215.64. So Apple had a little bit of a downswing in that particular year, 251.80. And we actually get a negative, so we kind of overshot the forecast a little bit, but we're not too worried about that at this point. Okay, so now we move on. We go in. We're going to go forecast for 2017. Forecast 2017 is our next task, and so I need the average for 2016. Now I get to roll with the formulas. Okay, I'm going to assume just initially. I'm going to assume an alpha is 0.6. A beta is 0.7. Okay, this is just my initial judgments. We'll learn how to use Solver in order to come up with mathematically optimal alphas and betas at least. Okay. So A 2006. Now I go alpha is 0.6 times by the demand. Now notice that the T in AT and the T in DT, they're the same. So that means they're occurring in the same year. So the average for 2016 is times by the demand in 2016. Okay? Plus 1 minus 0.6. And then the forecast for the previous period, which we had as 251.80. Okay, this demand for 2016, we just that's just a read off the table thing, 215.64. So we bring all that together, and that equals to 230.104. The trend for that same year, okay, smoothing constant of 0.7. Let's show the formula here. Trend, smoothing constant of 0.7, and then the difference between A 2016 minus A, or the average of 2015, plus 1 minus 0.7, which is 0.3, times by the previous trend, which was 18.08. Okay, average from before we see up above was 230.104. The average from 2015, we did make a little bit of a bootstrap estimate for that one, and that was 233.72. So the trend for 2016, we run through, we crunch all the fancy numbers, and we get 2.8928. So the forecast for 2017, we just add those two numbers up. 230.104 plus the trend of 2.8928, and our lovely little forecast for that particular year, 232.9968. What did we actually have for 2017? 229. Yeah, not too bad, right? Not too bad at all, actually. Not too bad at all. So let's continue on with our theme of repetition. Let's find the forecast for 2018. Okay, so we need the average for 2017, which has got its smoothing constant of 0.6, times by the demand for 2017, which is 229.63, plus 0.4, well, again, that's 1 minus 0.6, times by our previous estimate, previous forecast there, of 232.9968. And that average works out to be 230.7367. The trend for 2017, smoothing constant of 0.7 times by the difference between average in 2017 and the average in 2016. So 230.7367 minus 230.104 plus 0.3 times by the previous trend of 2.8928. Trend for 2017 revealed to be 1.3107, making the forecast for 2017 equal to 230.7367 plus 1.3107, and final answer. Suspense is killing me! 232.0474. There's lots of moving parts in there. Trust me, real easy to make a silly mistake in all this, by the way. All right. Next step. We've got our forecast for 2018. Right, 2018. Now we want our forecast for 2019. Forecast 2019. To find that, I need the average for 2018. And that is 0.6 times by 265.6. And then plus 0.4. And then times by our previous forecast. That number equals to 252 that is a 2, by the way, 179. And then the trend for 2018, 0.7, because that's the smoothing constant. The differences between the two averages, so the 252.179 from before minus the 230.73, if I could only write, 7367, plus 0.3 times by the previous trend of 1.3107. trend for 2018 revealed to be 15.4028, making our lovely 2019 forecast equal to 252.179 plus 15.4028. Grand total is 267.582. How did we really do? Inquiring minds want to know. Forecast, 260 is real. 267 is our estimate. Not bad. All right. Let's continuing on with our lovely scale of repetition. Forecast for 2020. Who could forecast anything in 2020? Anyway, average 2019 is 0.6 times by the demand in 2019 of 274.52 plus 0.4 times by the previous forecast. Oops. I skipped it here. Sorry, my bad. I've got it all written down, but all these numbers flow together. 0.6 times by 261.7, which is the actual demand for 2019. Ooh, jumped the gun there. And then 0.4 times by the previous forecast, 267.582. And then the average for 2019, 263.1348. The trend for 2019, that ever-changing trend, 0.7 times by, again, the difference between the average in 2019, which we just calculated, minus the average in 2018, which we see calculated just a little while ago, and then added to 0.3 times by the previous trend, previous trend being $15 billion and a little bit of change. And the new trend, 12.289er, making the forecast for 2020 equal to 263.1348 plus 12.2899, and our big estimate for the forecast for 2020 was 275.4247. What was it in actuality? 274.52. Damn it! We predicted 2020. Yeah, you know what? If you could predict anything out of 2020, forecast anything out of 20, wow! Super cool! Maybe we got that crystal ball working after all. Let's push our luck. Can we do anything about the forecast for 2021? All right. Whew. All flush with ego after successfully predicting 2020. Let's go with the average for 2020. That smoothing constant times by 2020's demand of 274. Our actual revenues of 274.5. Plus 0.4 times by 275.4247. And so our expected average for 2020, 274, and a lot of change, 0.882. The trend for 2020, up, down, all around. All we know is it'll be crazy. 274. The differences between the two averages, both in 2020 and its corresponding buddy in 2019. 1, 3, 4, 8. Holy cow. Lots of numbers right here. Plus 0.3 times the the previous period's trend of 12.2899. Trend for 2020 still up by almost $12 billion, making our fearless 2021 forecast equal to 274.882 plus 11.91. And we boldly forecast that Apple's revenues for 2021 will be $286 billion and $792 million. Not so bad, right? Now, okay, a lot of repetition, a lot of brain sweat. We started to see the flow of how things kind of work together. But what's really neat, If you thought that was neat, what's really neat about the trend-adjusted exponential smoothie model is we can make predictions not just for 2020, we can make predictions for 2022. Right? Before, with the exponential smoothie model, we were really restricted to making predictions in the next period. Okay. So if we had information up to 2020, we could predict 2021, but we didn't really have the quant tools to predict 2022. Trend-adjusted smoothie models, we do. We just take the 274, right, the average, plus, because now when we went 1 year into the future, we multiplied the trend by 1. If we go 2 years into the future, we multiply that trend by 2. And now we get our fearless, if I can only write, our fearless forecast for 2022 of 298,702. We could also make a fearless forecast for 2023. Again, we just take the same average of 274.882 and then add to it 3 times the trend, right? And we get whatever. And we can do the same thing for 2024. Right? Equals to 274. Again, same starting point. 882 plus, because it's 4 years into the future, 4 times by the trend. Now, as we get further and further out to the future, right, this estimate becomes murky because it becomes a lot more variable, because we saw that the trend is changing. It's not an extreme change to trend once we've sort of reached a certain point. We're fluctuating around 11 or 12 billion dollars. But, we see that there is there's some fluctuation to the trend. And we don't know, in the future that trend can change as well, depending on whether how Apple's new product developments work out and so forth. So given all those caveats, but we actually can have sort of a crude estimate for where we see things happening in 2021, 2022, 2023, 2024. Because remember, when you're planning your supply chain, you have to sort of be looking somewhat forward. You have to be somewhat forward-looking through this entire process. Okay, so that's the wonders of the trend-adjusted smoothie model, is that we can make those forecasts further into the future. Okay, so again, because this is just missed so much times, because I almost always ask a question about this on an exam. Whenever you're going to make forecasts beyond the next period, we just multiply the trend estimate by the number of additional periods. Exactly what we just did, and then add that to the average that we calculated. So it starts off with the same base. We just multiply the trend by a different value, depending on how far into the future we're going. So that's important, right? That's very, very important. Okay. We can use Solver to find the mathematically optimal values of alpha and beta. By mathematically optimal, I mean the ones that minimize our an error estimate, which we'll talk about in a subsequent forecasting segment. Okay, now the next pattern that we'll talk about is seasonal patterns. So we got the trend adjusted. We've adjusted for any trends. Now in our next segment, we'll talk about what's within a year. Right here, we're doing it year by year by year. What happens if there's those fluctuations within that year, or within a month, or even within a week? Right? How do I adjust for that? Well, we'll learn one such method in our next segment.